In this lecture, we're going to move to the next stage of dealing with multiple particles in a system. That is, when we have very large numbers of particles in a system, and therefore we deal with them statistically. And that will lead us to the very well-known and very useful Fermi-Dirac and Bose-Einstein distributions. The sources for this material are in section, it's actually, I believe, 7.3 in Townsend, and chapter 10, beginning of chapter 10 in Crane. We'll just have an introduction during this lecture, and then we'll talk a little bit about the midterm examination. And after the midterm examination, after the break, we will delve into the specific cases that are related to Fermi-Dirac and Bose-Einstein distributions. So first, quantum statistics. As I mentioned, there are going to be a number of related topics that deal with quantum statistics. We're just going to introduce the key ideas here, and then after break, we'll address specific special cases that are very frequently the most important special cases. So in dealing with multiple particles, we have worked on and thought about the electronic configuration of electrons in an atom. And I'll just mention now that as we move into solid state physics and many particles, that most of the bands of states that we find in solids, we'll talk about energy bands, are closely related to the original energy levels of the atoms that make the solid. And what we're allowed to do in filling up the states, as we discussed, is put one electron per state. There are two spin states per principal and angular quantum number here. So the 1s state can have two electrons in it because they are in different states when we put them in spin up and spin down, and so on. So we figure out how many electrons are permitted to be on a copper atom. The atom is neutral, determined by the charge of the nucleus. And just start adding electrons, putting them in the levels in order according to Hund's rules. I'll just mention here for now, later when we get to solid state physics, we'll be paying attention to the topmost band and how the topmost state is filled. If the state is partially filled, then it will turn out that the band of states into which this electron ends up is also partially full, and that will determine whether a material is a metal, a semiconductor, or an insulator. This particular picture that we've used so far is actually only correct at 0 temperature, when electrons go into the lowest energy state that is available to them. The question then is, what happens at finite temperature? Thermodynamics tells us that if the energy of a system is divided among a large number of particles, then all possible divisions of energies are equally likely. That is, individual particles can go into different energy states, subject to the rules of Pauli exclusion or not for bosons. So fermions, Pauli exclusion, bosons, no. Particle can go into certain energies, depending upon the rules. And then we look at all the ways that we can distribute those particles into different energy levels and have a fixed total energy for the system. Thermodynamics tells us once we have selected the energy of the system, that we have usually many ways that we can divide the energy up among a large number of particles in different states. So what we do is specify the energy of the system and then count up how a certain number of particles can be distributed in different energy levels in order to get that energy. That distribution tells us actually statistically how the electrons or bosons are actually distributed in the system. And there are different rules for different types of particles. The occupation rules are what's important here. If particles are distinguishable, then there's one set of possible ways that we can distribute particles. If they are indistinguishable, misspelled it there, sorry, then they are either fermions or bosons of one particular type. So they all the electrons, for example, then they're indistinguishable from one another, or indistinguishable bosons. And in those two cases, the particles will distribute themselves differently in the energy states because the rules as to how many can be in a state are different for those two types of particles. So let's start out figuring how many ways we can make a state, how many ways we can distribute 5 particles so that they have a total energy of 6. So here I've got 4 particles with 0 energy and 1 particle with 6. And if these particles are distinguishable, then I could take this one out and switch it for that one, and that would be a different state. I switch the next one, a different state. So there are 5 possible macrostates. 5 possible microstates. A macrostate would be one that's got 4 and 1, period. Just 4 and 1. And we don't distinguish how the particles are distributed in the 4 and 1. A microstate is one in which we distinguish one particle from another, and we say, oh, we switch this one for that one, that's a different state. Switch this one for that one, different state. So there are 5 different ways that I can achieve this distribution with 1 up here and 4 down there. 5 ways if I know that these particles are all different from one another. So I could label them particle 1, 2, 3, 4, 5, and put 1 up there, or 2 up there, or 3 up there, particle number. Right? Here's another way, B, that we could distribute 5 particles so that we get a total energy of 6. We put 1 particle in state 5, 1 particle of energy 1, and 3 and 0. And then we look at all the permutations. How can we switch those out? And how many ways are there that I could distribute those 5 particles in order to get that particular macro state? 1 here, 1 there, and 3 down there. There are 20 ways to do that. Similarly, there are 20 ways to distribute the particles into energy 4, energy 2, and 3 particles in energy 0. There are 30 ways to put 2 particles in the 0 state, 2 particles in the 1 state, 1 energy state, and 1 particle in 4. 60 ways to do this particular distribution. 2 at 0, 1 at 1, 2 at 2, 1 at energy 2, and 1 at energy 3. 60 possible ways to shift those around, right? And then we continue along, and as we continue, we get fewer and fewer possible ways to distinguish the particles from one another, depending upon how many we put in any one state. The actual way of counting up is to use a permutation, as we show down here. So what we would say here is that this state, which has got 3 particles distributed in energy 1, energy 2, energy 3, and 2 of them in the lowest state, is actually the most probable configuration of the system. We just allowed the system to have a given total energy and then measured an identical energy system many, many times with 5 particles in it. We would find the most frequent event would be the one that has this distribution of particles in it. The infrequent event would be one where we got 4 particles in the lowest energy state and 1 in the highest energy state, or the other way around, 4 in in a near low energy state but not entirely low, and 1 in a different energy state. So we have improbable events, finding these distributions of particles, and a probable event, more probable event, finding this distribution of particles. That is essentially the statistical way of dealing with this system. Again, thermodynamics tells us that each way of this occurring, one of these 5 ways, or one of these 20, or one of these, each one of those is equally probable. What that tells us, by the way, is that there's a low probability of finding a particle in this system in energy level 6. So we just turn the whole thing around, what we just did, and calculate for a given total energy the probability that a certain particle is in a certain energy state. And this can be done in this example by considering the collection of all 210 possible microstates and counting the number of times each value of the energy appears. So how many times do we see a particle in, what's the probability that we'll find a particle in state 6? What's the probability, and by the way, then it's 5 out of 210. Probability that we find a particle in state 5, 20 out of 210. Probability that we find a particle in state 4 would be 20 plus 30 out of 210. Okay? So we see the probability of finding the particle in a state increases as we go to lower energy. So here's the situation if we have distinguishable particles up at the bottom. So a slightly different way of looking at the same thing that we were just doing. In energy 1, we have a number of particles. In energy 2, we have a number of particles. In energy 3, we have a number of particles. And we call this energy 1, 2, 3. Okay? And we ask ourselves, how can we put these particles together in order to get a total energy of 8? Well, you could put 5 in the lowest energy state and 1 in the energy state 3. So 5 plus 3 would be 8. If these particles are distinguishable, then there, in this particular case, because there are a total of 6 particles, there are 6 ways of distributing. Okay, I can put particle A up here, or B, or C, or D, or E into the higher energy state. 6 ways of doing this. Here's another way, another macro state of the system, which has 4 particles in energy 1 and 2 particles in energy 2. Still a total energy of 8. And then we count up all the ways that we could put 2 particles in energy 2, and leaving 4 behind. So I could trade out particle E for one of these. Right? So there are 5 different ways to do that. Okay, and then there are 4 different ways to switch out F, given that we have. Oh no, I take it back. Actually, I don't know off the top of my head the number of ways, but it's going to be multiplied by the number of ways that I can switch out particle F. But now, if the particles are actually indistinguishable, then we'll call all the particles particle A. Then this energy with 8 energies, 8 E1s, it has particle A, and A in the base bottom state, and particle A in the top state. There's only one way to do that. If I switch one of these out, it's the same thing. So there are only 6 ways to do this. Oh, sorry. There's only one way to actually achieve this particular macro state with 5 in the bottom level and 1 in the top level, because switching them out doesn't change the state at all. Similarly, there's actually only one way to do this. So if the particles are indistinguishable, then there's only one way to arrange the particles into a particular macro state with 5 and 1, for example. There are quantum rules that we learned previously are that we can only put 2 fermions spin up and down in any microstate of the system, but we can put an infinite number of bosons into any microstate of the system, subject to total energy. So given our total energy situation, we're only allowed to put 2 fermions in energy 1, 2 in energy 2, 2 in energy 3. So when we look statistically at what that tells us about the distributions that occur for different occupation and distinguishability rules, right? If we're allowed to put as many particles as we like into any given energy, but the particles are distinguishable with no quantum mechanical occupation rules, the statistical distribution that we would get for the type of system that we were just looking at looks like this. It sort of looks like an exponential decay away from some particular energy, which we'll distinguish in a moment. For bosons, right, for our 6-particle system that we were looking at, so counting up how many ways can we distribute particles in various ways, right? What's the probability that we find a particle in the lowest energy state, the next state, the next state, and so on, right? What are the rules for that? And we end up with a distribution that looks sort of like that one, but not exactly the same. But when we have the rule that we are only allowed to put 2 fermions into each energy state, starting at the bottom and working our way up, then the statistics of how frequently we find a particle in a given state change dramatically. You can see here. We can look at what happens with very large numbers of particles, and that's what we mean when we're talking about quantum statistics. On the previous slide, when we looked at how the distributions looked for a finite number of particles, we only had 5 or 6 particles in the system, and then we looked at the probability of finding a particle in a given state. We found that when particles were distinguishable, it had a slightly different distribution from when particles were indistinguishable from one another, and we could put a large number of particles, no rules, in any given state. So bosons and distinguishable particles don't look tremendously different for that finite number of particles. But when we start considering much larger number of particles, it turns out that there will be a difference that appears. And the distribution for fermions was quite different because we're limited with respect to how many we can put into the low energy states. So this leads us then, as we analyze large numbers of particles, to 3 distributions, the actual mathematical distribution functions. The first is the Maxwell-Boltzmann, which, to be honest, is just an approximation because basically everything is either a boson or a fermion. And we actually should analyze all systems this way. But for relatively massive particles, for example, atoms, so not electrons or photons, but particles that have large masses with relatively low energies, it turns out that a Maxwell-Boltzmann distribution, which is the one that you learned about in chemistry, is a reasonable approximation to the distribution of particles in a system. So the particle distribution we label with a small f, so this is called the distribution function. The probability of finding particle in a particular energy state as a function of energy is the exponent, e to the minus energy of the state minus what's called the chemical potential of the system divided by kT, where K is the Boltzmann constant. So this should actually be labeled as K sub BT, and I was a little bit sloppy about it. So K times the temperature. So energy and energy difference, so an energy measured with respect to something, that's called the chemical potential, right? Divided by the temperature, basically, with scaling. The Bose-Einstein distribution, F sub BE, is 1 over the difference in energy between the energy of the state that you're analyzing and the chemical potential of the system, divided by kT, minus 1. I'll show you what these distributions look like in a minute. This actually does look quite a bit different from this one for low energies. Energies close to the chemical potential of the system. And then the Fermi-Dirac distribution, which applies for fermions, electrons in particular is the important particle for us, is the distribution is 1 over the energy difference between the state of interest and the chemical potential of the system, divided by kT, Boltzmann constant, plus 1. And that distribution is quite a bit different from those. But at high energy, these two all look a lot like one another. If the energy here is the energy difference between the energy of interest and the state of interest and the chemical potential, if that difference is large compared to kT, then here, of course, this actually does look e to the minus e energy minus chemical potential over kT. This one here, when the energy difference becomes large, then this term dominates, and this looks like e to the minus e minus mu over kT. And when e minus mu over kT is large, this term dominates. So all of these two reduce to this one for energy much larger than the chemical potential compared to kT. To go through particles one by one. Bosons are quantum mechanically indistinguishable particles. We're allowed to put any fraction into one state, and we have some additional considerations that actually lead to rules that tell us what mu can be, what the chemical potential can be. And one of them is called the principle of detailed balance. That is that in thermal equilibrium, the rate at which particles transition upward between a lower energy state and an upper one, and downward, has got to be equal. And that helps to determine what the constants are. Fermions are indistinguishable particles. We're allowed to put only 2 particles per energy state. And same principle of detailed balance. Put all of that together, we end up with with statistics, and we end up with a distribution that looks like this. On the next slide, I'll show you a sketch of these. So in the low energy range, what we're plotting here is the number of particles in a given state, in an energy state, versus the energy of that state. In this case, we've scaled the energy to kT, to the Boltzmann constant times the temperature, in Kelvin. And we're taking the difference between the energy of the state and the chemical potential of the system. So at this particular point, the chemical potential, energy minus chemical potential is 0. So 0 and up. Numbers down here, E minus mu over KT is small, and over here, E minus mu over KT is large. You can see that these three distributions collapse to one another. They get very close to one another for large energies, but at small energies, they diverge. Small, again, relative to KT. The Bose-Einstein distribution increases exponentially toward 0. So the a state with 0 energy relative to the chemical potential will have an infinite number of particles in it, subject to total energy of the system being a certain energy. The Maxwell-Boltzmann distribution looks like this, and the Fermi-Dirac distribution is quite a bit less likely to find a particle in a low energy state than either Bose-Einstein or Maxwell-Boltzmann. Again, that's because we're limiting the number of particles that can go into low energy states using the fermion rules, only 2 into a particular energy state. At E minus mu, at E energy equals mu, the probability of finding a particle at energy equal to mu is 1/2. If we analyze that equation, it will turn out to be 1/2. For the Bose-Einstein, it's infinite. The Fermi-Dirac distribution, when we actually look at energies below the chemical potential of the system, asymptotes to 1. The probability of finding a particle in an allowed state is essentially 100% when that energy is much less than the chemical potential of the system. At 0 Kelvin, we call the chemical potential, chemists call the chemical potential the Fermi energy of the system. And this particular drawing here is illustrating another idea that I don't want to go into at this point, which is how the Fermi energy shifts with temperature. Chemists don't use Fermi energy for anything other than 0 temperature. Physicists and electrical engineers actually just regularly call the chemical potential of the system the Fermi energy of the system. The one thing that we've got to keep in mind is that the total number of particles in the system, when we set a system up, is fixed. And as we change the temperature of the system, we change the distribution. And as a result, there are probability effects that come about because we can't have more particles than we started out with. And if we left the Fermi level always at one particular position independent of temperature, then we would find that the number of particles in the system changed. When we're counting particles, we have to ask how many available states are there in a certain energy range. And that's called the density of states. We will talk about that more after the midterm break. So the Fermi energy of a system is the energy at which the probability of a state being filled is 1/2. And a simplification for 0 Kelvin is that at 0 Kelvin, the Fermi energy is the highest energy state that has a particle in it. Figuring out what's going on with atomic states, which are well separated in energy, is easy, but counting states and filling states for something like a metal with 10 to the 23 particles is hard without an approximation. The approximation that we use is the density of states. So coming back to that electronic configuration of the copper atom, right? We have some idea now of, I talked about density of states. How many available states are there in a certain energy range? So in this energy range here, there are only two available states, one energy state. Only two available angular momentum and energy states here at the 2s level. The 2p level, the density of states is increased by a factor of 3 because now we have angular momentum, different angular momentum for different states. 3s, only 2, 3p, 6, 3d, 10. You can think of these numbers here as being the density of states. How many states do I have in a certain energy range? So looking at filling atomic levels, we can connect this to the statistical distributions that we were looking at. Density of states, how many are there in a particular energy range, and Fermi level is the energy of the state, which is the last one filled as we go up. So the Fermi energy or Fermi level for this system would be near the 4s level in this particular system. I'm going to talk a little bit right now about the midterm examination, but I'm saving this for discussion during class because I want you to ask questions. There are a few things that I can just tell you. The midterm will be in class on Friday, unless you've made some prior arrangement in the event that you can't actually be there for good reason. If that's the case, then I can permit you to take it in another 2-hour window, but it will be a 2-hour window. I prefer to have it in class so that we don't conflict with other examinations. The submission of the exam is somewhat similar to the way that you've done activities and quizzes. The exam will be about 50%, let's say between 40 and 60%, multiple choice and short answer, something that I can grade quickly within LMS, right? Maybe less than a sentence or less, or an equation. And that'll be somewhat, probably a little bit more than half, but around half the points on the examination. That will be mostly auto-graded and quickly graded in LMS. And then about 50% of the examination will be a longer answer where you will submit that either by writing something in a text editor and converting it to a PDF, or writing it by hand and taking an image and submitting that as a PDF through LMS the way that you've been submitting it. So there'll be two parts to the midterm examination. The topics are listed on the following pages. I reserve the right to add a topic if I have forgotten one. That will happen in class on Tuesday. So we started this course talking about numerical methods, but we're not emphasizing that in this examination. You won't be writing code in this examination. We talked about the first important thing that we talked about here were hydrogenic wave functions and spherical potentials, the situation for spherical potentials where the angular solutions lead to associated Legendre polynomials and spherical harmonics. Those are the same thing. They're not the same thing. This is a normalized relationship that includes the azimuthal angle phi. Associated Legendres are just in theta. And the important quantum information, quantum numbers that come out of this are the angular momentum quantum number and the magnetic moment quantum number, L and M sub L. For the Coulomb potential, we have a set of radial solutions that apply, and we can deduce the energy levels for that system and the angular momentum and count up the number of modes. The second important topic that can be included on the midterm examination has to do with the probability of optical transitions. And I went through it quickly, a derivation using time-dependent perturbation theory, but that is not the most important thing for it's not an important thing for this examination. It's a question of your being able to understand and use the results of that time-dependent perturbation theory. Those results have to do with selection rules and the probability of a transition happening when it is of a certain energy and you allow it a certain amount of time to occur. The probability of a transition that is occurring depends upon computing what's called the matrix element for the transition, which for a dipole transition, that is something that has to do with an electric field, depends upon the integral of a linear Cartesian coordinate, for example, x, that's the polarization of the light, times wave function 1, the initial state wave function, times the wave function of the final state that you were considering. That's what's called the matrix element. And for simple cases, you should be able to evaluate whether the matrix element is 0 or finite. You don't necessarily, I wouldn't be expecting on the midterm for you to do a full computation, but more to prove that something is 0 or not 0. The second portion of computing the probability of transition is to consider the energy difference between the initial and the final state and the excitation wavelength for light coming into a system. And that leads to a time-energy Fourier transform relationship, which is related to the Heisenberg uncertainty principle. And you should understand how to do these sorts of integrals and to interpret the results of these integrals. Basically, Heisenberg uncertainty principle for time and energy. Computing this spatial matrix element leads to selection rules for whether a transition can occur by an electric dipole excitation or not. The first and most general of these selection rules is the parity selection rule. That is, whether the wave function is even or odd, relates to whether the initial and final state wave functions are even or odd, relates to whether the transition can occur or not. Usually for a dipole transition, the parity of the initial and the final states must change. That actually turns out then to be related to the angular momentum for spherical potentials. So parity and angular momentum are connected to one another, but angular momentum is only a good quantum number for a spherical potential. So we have selection rules for whether a transition can occur or not, depending upon the change in angular momentum for the initial and the final state. And that then also relates to the change in magnetic quantum number for initial and final states. And then finally, we did not prove, but we stated that the spin quantum number cannot change under an optical excitation, but the projection of the spin on an axis can change. We then moved into the topic related to dealing with systems with multiple particles in it. When you have multiple particles, you have to consider whether those particles are identical or not. And we introduced the idea of exchange symmetry. When you exchange two particles in a system, does the sign of the wave function change? We found that we needed a more complex wave function if we want to ensure that the wave function has the same probability density before and after the exchange. If the particles are exchanged, the probability density must be the same. That led to the concept of wave functions that are symmetric and antisymmetric under exchange of particles and the exchange pseudoforce. That is, that for symmetric particles, on the average, particles are found closer to one another than for antisymmetric space wave functions. So, symmetric space wave functions antisymmetric space wave functions. Fermions require antisymmetric overall wave functions, and bosons require symmetric overall wave functions under exchange. I just remind you here that you should keep track of both the spin and the spatial part of the states that you're looking at. Once we had those rules in place, which led to the Pauli exclusion principle, then we can consider what happens for electrons, for multiple electrons in an atom. We analyzed the helium atom fairly closely and identified an effect which is called screening or shielding, where an electron on an atom can spend some time inside the orbital of another electron and therefore screen the other electron from the charge of the nucleus, changing the energy for that state. So you don't have simply hydrogenic states any longer. The second electron has to use the potential of the first electron in order to set its energy and wave function. Then, once we had the rules and the effects of screening, we can look at the systematics of atomic properties. This is not so quantitative, but deals with Hund's rules, that is the order in which orbitals are filled, and getting some idea of what the approximate energy levels would be. It's always a very rough estimate. This might be based upon some screening effect, for example, Slater's rules. And thinking about the outermost electrons in the system and how those electrons are bound to the nucleus, and basically whether they are screened by electrons in lower energy or other states. Right? And the patterns then deal with the outermost electrons, in which we measure the ionization energy, for ionization being the smallest excitation that will remove an electron from a system, for the outermost valence electrons, and X-ray emission and absorption for the core electrons. Once we had the rules in place for understanding the states of atoms, we can begin to think about how molecules are made up and what controls and allows us to estimate the wave functions and energies for electrons in molecules. We discussed the idea, we used the hydrogen plus ion, that is 2 protons with 1 electron, in order to understand the principles behind covalent bonding, where an electron is shared between 2 nuclei. One of those principles is the Born-Oppenheimer approximation, which is really simple. You just assume in Born-Oppenheimer that the nuclei are not dynamically moving, so you don't have to solve for the wave function of the nuclei. You treat them classically. An approximation for figuring out what the energies for electrons on a covalent atom system are, molecular system are, is what's called the linear combination of atomic orbitals, where you take the orbital that you solve for the individual atoms, and you use those, the relevant states, for example, the 2p state, as the basis for making a linear combination of these orbitals in order to approximate the covalent bond, the way that the electron is distributed over the 2 atoms in a molecule. That led to the idea of bonding states, which are normally the states, electron states, that are symmetric, even with respect to the electron being on one atom versus the other atom, and anti-bonding states in which the wave function is an odd function with respect to the wave function of the electron on one atom versus the other atom. Then we added the second electron to make a hydrogen molecule, and talked about this in only a semi-quantitative way, because doing the full calculation is actually beyond the level of this course and would be intensely computational. We talked about the concept of covalent bonding with s orbitals and p orbitals and d orbitals and mixtures of those orbitals that lead to different geometries for the bonding between multiple, more than two atoms in a system. As an approximation to covalent bonding and also a useful approximation to ionic bonding, I introduced what's called the Morse potential, which is just empirically fit to the way that systems behave, but it's actually not too bad as an approximation to the energy of a molecular system as a function of distance between the two atoms. The second topic that we talked about was ionic bonding. In the simplest case, we take an electron off of one atom, put it on the other atom, and then consider the Coulomb attraction between those two ions. So there's energy to remove the electron from one atom, energy that you get back to add the electron to another atom, plus the Coulomb attraction. Corrections that have to be made to that include quantum mechanical effects due to wave function overlap. The final type of bonding that we talked about here, there's one more after this, it's called metallic bonding. But the final type that we talked about in this course is called van der Waals bonding, and that has to do with spontaneous polarization of atoms. There's no exchange of electron, but the polarization gives rise to a field that causes atoms to interact and bond very weakly to one another. So covalent and ionic bonding are typically strong interaction bonds, and van der Waals bonding is a very weak interaction. Materials that form van der Waals bonds frequently evaporate or melt, so they cease bonding at room temperature. And then finally, one of the tools for figuring out what all these bonds do, what's the depth of attraction, what's the potential depth, and what's the shape of the potential well, can be addressed by looking at the vibrational spectra. And we looked at a very simple case there, assuming that for small amplitude vibrations, that the system is a harmonic oscillator. And then earlier today, we talked about quantum statistics and how distinguishable versus non-distinguishable particles have different distributions. Distinguishable is Maxwell-Boltzmann. Non-distinguishable are Fermi-Dirac and Bose-Einstein. At large energies compared to kT, Fermi, all of these are the same, but at very small energies relative to kT, the Fermi-Dirac and Bose-Einstein distributions are quite different.